Okay, we'll get started today. We're going to move on with chapter 6, keep going through and talking about solution reactions. Alright, so last time we started with defining just some basic properties of solutions themselves, and now we're going to start talking about different types of chemical reactions that happen in solution and primarily in aqueous solution, which are solutions in water. So this part of the chapter, the sort of middle part, which we'll cover today and Friday, deals with three major types of reactions, three major classifications. We'll cover the first two today, and we'll cover the last of those on Friday. So the idea here is we're going to learn about the different types of reactions, learn how to predict the products for some of these reactions, and then also learn how to balance them, which is what we're going to talk about mostly on Friday. Okay, so let's get on with what we have to cover today. So the first thing we have to start with is some definitions. So we're going to start with the first major category of reactions, which is precipitation. So we're going to talk about precipitation reactions, and we're going to define those first, and then give you some examples and some things that we should be able to predict about these types. So the definition of a precipitation reaction is we're going to take two aqueous solutions and combine them. And then when we combine these two aqueous solutions, so remember that the solution means that the ionic compounds are dissolved. And so they're starting out in solution, but when we combine them, one or more insoluble products forms. Usually it's only one, but sometimes you can get two insoluble products. And that means that there's something that forms during the reaction that is not soluble in water, and it forms a solid or a precipitate. And these are going to involve ionic compounds. So when we're talking about precipitation reactions, our first clue that that's what we're talking about is that we're going to be combining two solutions of ionic compounds. All right, so if we want to determine whether a precipitate will form, there's a few steps we can follow, because really that's the major thing we're going to have you do on homework problems and test problems, or one of the more difficult ones, is we'll give you a precipitation reaction or set of reactants and say predict the product or predict what the precipitate is. So the first thing we have to do is separate the reactants into their constituent ions. So we're going to have two ionic compounds that we're combining, and we want to think about what are the individual cations and anions that make up those ionic compounds. All right, so let's work through an example then of all these steps. So let's say we combine potassium iodide as an aqueous solution, and we're going to mix that with lead nitrate, lead 2 nitrate to be more specific. So we mix together two aqueous compounds that are in solution. And then what we want to think about is what are the ions that make up those aqueous compounds. So when we dissolve these, Ki is made up of potassium plus and I minus. So we have K plus I minus from the potassium iodide. And then for lead nitrate, we have lead 2 plus, Pb2 plus. And then if we want to be careful with stoichiometry here, lead nitrate has two NO3 minus anions. It's NO3 taken twice, so when that dissolves, we're going to get two equivalents of NO3 minus. Okay, so those are all the ions we have. We have K plus, I minus, lead 2 plus, and we have two equivalents of NO3 minus. So we consider all those possibilities, and then we want to find all possible combinations of the cations and anions with each other. So we swap the cations and the anions. So K plus, which this cation started out paired with I minus, and now we're going to pair it with the other anion, which is NO3 minus. So usually when we consider all these combinations, you're going to have two possible products where we're just going to swap the cations and the anions. So when we pair this cation K plus with the other anion, which is NO3 minus, we get KNO3. And then when we pair the other cation, which is lead 2 plus, Pb2 plus, with the other anion, I minus, we have lead 2 plus, I minus, so the formula for that would be PbI2. So basically we're forming two new ionic compounds where we're taking the cation from one, combining it with the anion from the other. We're taking the anion from the first compound and combining it with the cation from the second compound. So we're just swapping cations and anions with each other. And then the question becomes, okay, we formed these two new ionic compounds, KNO3 and PbI2, and then are either of those, or are both of those, going to be insoluble? And to predict whether the compound is insoluble or not, we have to learn this set of rules called solubility rules, which, if you're not groaning already, you will be in a second, because this is one of the worst parts of general chemistry. So there's a set of rules you have to learn. Now, many people just approach it as a random list of rules that they just have to memorize, but I'm going to try to give you a little bit more of a systematic way to think about it. And when we're looking at solubility rules, there's a few obvious rules we should think about first before we start worrying about a lot of the little intricate details. Okay, so how do we go about this in a more systematic way? So your book has a list of solubility rules, and I believe I reproduced it in the notes later on. But let's think about a little bit of a simpler way to break it down. So when you're considering the solubility of an ionic compound, the first thing you can do is look at certain cations and anions that will always form soluble compounds. So if you have either that cation and or that anion paired together, you're going to have a soluble compound. So there's a few cations that fall in this category and a few anions. So most of the always soluble cations are going to be those from group 1A on the periodic table. So that's going to be lithium plus, sodium plus, potassium plus, rubidium and cesium. So all those group 1A monocations. And then there's one more, which is a little bit weird, but NH4 plus, ammonium, a polyatomic cation. So if your compound has one of these cations in it, it doesn't matter what the anion is, it will be soluble. You don't even have to think about the anion. And then finally, there's some anions that have the same property. So this list of anions here, if your compound has one of these anions, it will be soluble no matter what the cation is. So those are going to be NO3 minus, ClO4 minus perchlorate, acetate, which we can write as either CH3COO minus, or sometimes it's written as C2H3O2 minus. That's called acetate. So those three anions, if you see them in an ionic formula, you can automatically assume that that compound is soluble, regardless of what the cation is that's paired up with it. So category A, so if you see one of these cations, one of these anions in the compound, you know it's soluble, you don't have to think anything more about it. There's also a category of ions, primarily some cations and some anions, where they're going to be always insoluble unless they're paired with one of these special cations or anions. So the cations that fall in this category are silver plus and lead 2 plus. Alright, so if one of these cations is paired with anything else besides nitrate, perchlorate, or acetate, you can assume that it's going to be insoluble. So whatever the anion is, if it's not one of these three, that'll be an insoluble compound. And then there's certain anions that always give rise to insoluble compounds unless they're paired with one of these special cations from group 1A or ammonium. So carbonate, CO3 2 minus, phosphate, PO4 3 minus, sulfide, S2 minus, and a weird one, chromate, CrO4 2 minus. So these four anions are going to pretty much always give insoluble compounds unless they're paired with one of these special cations here. Okay? So those are the two really obvious rules that you should think about first. Whether it's going to fall in one of these two categories when you can automatically identify it as being soluble or automatically identify it as being insoluble. Now there's some other rules then that we should think about that are a little bit more of gray area involved. So we have another category which is primarily anions, which are usually soluble unless paired with one of the cations from category B. So the halides, in particular chlorides, bromides, and iodides, those usually give soluble compounds unless they're paired with one of those cations, silver plus or lead 2 plus, one of those cations that always makes insoluble compounds. And then there's some other exceptions to the soluble halides as well that we should be aware of. So copper plus and mercury 1, which is a weird one, is a polyatomic cation with 2 mercury plus 1s together. These are also examples of insoluble halides. All right? But basically, if you have a chloride, a bromide, or an iodide, you can expect it to be soluble unless it's paired with lead, silver, copper, or mercury. All right? If it's anything else besides those 4, you can assume that the halide would be soluble. And then finally, there's another category, which is the ones that people often get tripped up on, the sort of in-between annoying ones, where, yeah, sometimes they're soluble, sometimes they're not, and you're just going to have to become familiar with them. So there's sulfate, SO4 2-. This one is usually soluble, but it has more exceptions. So it's soluble unless it's paired with one of those category B cations, which is silver and lead 2 plus. So, or if it's also paired with calcium, strontium, and barium. So these heavier group 2A cations form insoluble sulfates. All right, and then finally, hydroxide, OH-, is usually insoluble. So, but unless it's paired with category A, which are those special cations, lithium, sodium, potassium, all those, ammonium, or it has the heavier group 2A cations as soluble exceptions. So these are the same exceptions as above, but this time they make soluble hydroxides as opposed to insoluble. So calcium, strontium, and barium, again, are the exceptions. With hydroxide, they're soluble. With sulfate, they're insoluble. So these are the ones that are a little bit trickier to remember. But the other point to keep in mind is that these rules kind of form a hierarchy. So, like I said, I gave them in this order for a reason. Look at group A and group B first. Look for the obvious, always soluble ones first, or look for the obvious, almost always insoluble ones first, and then you can start, if you need to, thinking about some of these weirder exceptions. All right, so then you'll need to become familiar with those. There's not really, I try to help you learn them in a bit of a systematic way, but you really just have to become familiar. So here's the list that's in your book, which again is broken down into 6 categories instead of 4, so it makes it a little bit more complicated, but it should follow the same rules that I just gave you above. All right, so now that we know something about soluble and insoluble products, we can start talking about how we write reactions for precipitation, for combining 2 ionic compounds, predict the product, and also balance them. So there are 3 ways that we can write the chemical equations for any aqueous reaction, really, but we're going to apply it mostly today to precipitation reactions. So the one that we always start with, or the easiest one to think about, is what's called the molecular equation, or sometimes called the formula equation. So in this case, we write both the reactants and the products as intact compounds. In other words, we don't separate the ions in this type of equation. And this is usually going to be your starting point, because this is where you write out the full reactants, and then you write out what the expected products are, and you don't really separate ions at this stage. So going back to the example that we had before, if we take potassium iodide, when we're doing precipitation reactions, we're always starting with soluble ionic compounds, so it's going to be aqueous, dissolved in solution. We combine that with lead nitrate, which is also soluble. And again, thinking about our solubility rules, we have K plus is always soluble, so we know that potassium iodide will be soluble. And then NO3 minus is always soluble, so we know this will be soluble. But anytime you're doing a precipitation reaction, you're always starting with 2 soluble compounds. And then we form products. We have, as I said, we pair the first cation with the second anion, so we get KNO3. And then our second product is going to be the first anion I minus paired with the second cation lead 2 plus, so we get PbI2. Now if we think about solubility rules here, K plus and NO3 minus are always soluble, so we can write that still as an aqueous species. It's dissolved in solution. But then PbI2, remember that lead 2 plus compounds are almost always insoluble, so lead halides are insoluble. And so this is going to be our precipitate, so we put a little S after it to tell us that it's forming as a solid and it is no longer dissolved in the aqueous solution. So that's how we sort of write it out, but now we need to balance. So usually precipitation reactions are pretty simple to balance because the coefficients tend to be pretty small. But if you look at this here, we have 2 NO3 minuses paired with lead, so we're going to have 2 KNO3s. We have 2 iodines, so we need to put a 2 in front of Ki. And that should be all we need to do to balance this. So balancing is usually pretty simple, but you do need to look and make sure that the number of ions on the left equals the number of ions on the right. And so a couple of coefficients are needed in this case to do that. Okay, so that's what we call the molecular or formula equation. Now the next type of equation we can write for aqueous reactions is called the total ionic equation. So in this case we separate all soluble ionic compounds into their ions. So anything that has an AQ after it in the total ionic, in the formula equation gets separated into ions in the total ionic equation. So anything that's dissolved as an ionic compound, remember, is going to separate into individual cations and anions. And so in the total ionic equation, that's what we're going to write. So in this case here, on the reactant side, we have Ki, so that's going to split up, as we said, into K plus and I minus. So you have 2K plus and 2I minus, because this coefficient of 2 applies to both cation and anion. So you have 2K plus and 2I minus dissolved. Our other reactant is aqueous lead nitrate, so that's going to give us a lead 2 plus and 2 NO3 minuses. Okay, so those are all the reactants split up into their ions. 2K plus, 2A minus, lead 2 plus, and then 2 NO3 minuses because it's lead nitrate taken twice. And then on the product side, we look at what we have. KNO3 is still listed as aqueous. It's a soluble ionic compound, so we're going to write out, again, K plus is going to be separated as an aqueous ion. 2 NO3 minuses are still dissolved aqueous. But then our second product, PbI2, we said is insoluble. So we don't want to separate this into ions. Remember that insoluble products do not separate into ions. They're forming a solid here. So we still write that as PbI2 solid. So only the soluble species, only the ones that dissociate into ions get separated when we write the total ionic equation out. So that's the total ionic equation. We've taken everything that's an aqueous species and separated it into ions. And then finally, the net ionic equation, we have to remove what are called spectator ions. And these are going to be the ions which appear on both sides of the equation. Okay, so we find the ions that are on both sides of the arrow. So if we look at this up here, we have 2K pluses on each side, and we also have 2 NO3 minuses on both sides of the arrow. So K plus, potassium plus, and NO3 minus nitrate, those are the spectator ions, and when we write the net ionic equation, we just drop those out. Basically, because they're on both sides of the arrow, they cancel each other out. You have something on the reactant side and the product side. There's no net change involving that species, so we don't have to even write it. And so what we get then is just Pb2 plus. Conventionally, we write cations first and then anions, so it doesn't really matter. 2I minus. And those combine to form PbI2 as a solid. So when you write the net ionic equation for a precipitation reaction, only the ions that combine to make your precipitate are going to be the ones that you're including in the net ionic equation. And that leaves then, of course, K plus and NO3 minus are the spectator ions. which means there's no net change involving those ions. They're soluble ionic compounds on the left side, they're soluble ionic compounds on the right side, so they're called our spectator ions. So these are the three ways we can write equations for precipitation reactions, and you're going to want to be familiar with all of them, especially the net ionic equation. That's one that we'll certainly ask you about on homework assignments and tests, is how to produce the net ionic equation. So let's do one more example of that, just to see how it works. So we want to write the molecular, total ionic, and net ionic equations for the reaction that occurs between sodium sulfate and silver 1 nitrate. All right, so first we start with the molecular equation where we just write everything intact. So we have sodium sulfate is sodium plus with SO4 2 minus, so the correct formula is Na2SO4. So one thing you may need to review if you've gotten a little bit rusty on it are the formulas and names for ionic compounds. We talked about that much earlier in the course. I think it was, chapter 3 or so. So make sure you remember how to name and write the formulas for ionic compounds. But sodium sulfate is Na2SO4. That's going to be soluble because it has sodium in it. And then we combine that with silver nitrate. So silver 1 is Ag plus, nitrate is NO3 minus, so silver nitrate is AgNO3. Also a soluble compound because it includes nitrate. And then remember, for a precipitation reaction where we mix together two aqueous solutions, we have to think about pairing the first cation with the second anion, and then vice versa. So the second cation with the first anion. So what we get in this case is sodium gets paired with nitrate to make NaNO3. I'll leave the balancing coefficients out for now. So Na plus gets paired with NO3 minus to make sodium nitrate, which is going to be soluble because sodium and nitrate are always soluble. And then silver plus gets combined with SO4 2 minus, so we have Ag2SO4. And then this one here, it's a silver compound. Most silver 1 compounds are insoluble unless they're paired with nitrate, perchlorate, or acetate. So this is going to be our precipitate solid. So again, look for things like silver and lead because those are usually going to be involved in forming the precipitate. So this kind, again, the silver compound here is the precipitate, the solid. We have to do some things to balance this reaction. So we have 2 sodiums over here, so we need to put a 2 in front of sodium nitrate. We have 2 silvers here, so we need to put a 2 in front of silver nitrate. All right, so those coefficients, again, fairly small usually for precipitation reactions, but we have to make sure we include them if we want to balance it out. And then from here, we can write the total ionic equation. So all of these soluble ionic compounds, the ones that have AQ next to them, we're going to separate out into ions. So on the reaction side, we have Na2SO4, which dissolves to give 2 Na pluses, and an SO4 2 minus. We have silver nitrate. We have 2 of those, so we're going to get 2 Ag plus and 2 NO3 minus. And then on the product side, our Na plus and NO3 minus are still soluble, so we have 2 of each of those, 2 Na plus, 2 NO3 minus. And then finally we have solid silver sulfate. We don't separate that one because it's insoluble. Okay, so our total ionic equation is going to include everything that's soluble being separated out. So on the reaction side we have 4 ions. On the product side we have 2 ions that are still soluble, and then 2 that combine to form our precipitate. So that's the total ionic equation. And then finally, for the net ionic, we have to remove the spectator ions. So those are the ions that appear on both sides of the arrow. So we see that Na plus appears on the left and the right side of the arrow. NO3 minus appears on the left and right side. And we should start to see a pattern here because, as I said, Na plus always forms soluble compounds. NO3 minus always forms soluble compounds. So most often those will be spectator ions. Things that are always soluble will be listed as spectators. And so in our net ionic equation, what we're left with are 2 Ag pluses. Again, conventionally we do cations first. SO4 2 minus. And then on the product side we have the combination of those two, which forms a precipitate, Ag2SO4. All right, so once again, the net ionic equation for precipitation reaction is just the cations and anions that combine together to form the insoluble precipitate. Nothing else is included. All right, any questions on that? Okay, so we're ready to now move on to our next major category of reactions, which is acid-base reactions. This is something you will talk a lot about more in chemistry too, but we are going to introduce it at a fairly basic level here, pun intended. So we're gonna start with a few definitions. Of course, we have to know what an acid and a base are before we can talk about how they react. So there's a few different definitions of acid. You'll get more in detail on this next semester if you take chemistry too. But for our purposes, an acid is a compound that releases H+ when it's dissolved in water. So when we talked about electrolyte solutions last time, which are solutions that conduct electricity, we saw that acids, when you dissolve them in water, they do in fact conduct electricity, and that's because they do separate into ions in water. But one of the ions is always going to be H+, so it's not really a metal cation, but it's called a hydronium cation. And so an acid releases H+ when dissolved in water. And we talked about earlier also the nomenclature for acids. How do we name acids? And so as we saw, they all have the same general formula. So acids always start with hydrogen, some number of hydrogens, and then X, which is the anion. So it's going to be H+ paired with some anion, which can be either a simple monoatomic anion like chloride or bromide, or it can be a polyatomic anion like nitrate or whatever. And then the number of protons that you have, the number of H+ is going to be equal to the anion's charge. So there's a lot of similarities between acids and ionic compounds, because what you have is, again, H+ paired with an anion, and you have to have the correct number of H+ to balance the charge on the anion, whatever that is. Okay, so that's what the general formula for an acid, that's what they look like. Bases are compounds that release OH- in water. So the vast majority of bases that we're going to talk about, and really the vast majority that we use in aqueous chemistry, are going to just be hydroxide salts. So they're going to have some metal cation, M, paired with some number of hydroxides, OH-. Where again, the formula is determined by the charges. So N is the charge of whatever the countercation is. So a base is basically just a hydroxide salt. It's just a metal paired with hydroxide anions. When you dissolve it in water, provided it's a soluble hydroxide, you release OH- in the solution, and that's how we then categorize it as a base. Now within acids and bases, we have both strong acids and weak acids and bases, strong or weak. This is not going to be a terribly important point in this section, although there's some things we want to know about strong acids and strong bases versus weak acids and weak bases. So something that's strong is an acid or a base that dissociates completely. So an acid or base that dissociates completely into its ions is a strong acid or a strong base, and as we saw last time, these result in a strong electrolyte solution. So for an acid, if it completely breaks down into H+ and then the counter anion, that's considered a strong acid, and for a base, if it completely releases its OH-. So we want to be familiar with the strong acids and the strong bases that we'll see. We gave this list last time, so just to review it. The strong acids are the three heavier halogen acids, so it's going to be HCl, HBr, and HI. And then there's three of the oxo acids that are also considered strong acids. So we have HNO3, HClO4, which is perchloric acid, and H2SO4, which is sulfuric acid. So those three oxo acids and those three halogen acids are the strong acids that we need to be familiar with. There are some other more esoteric ones that we won't see. And then the strong bases are going to be basically your soluble hydroxide compounds. So any hydroxide that's soluble. Now, as we talked about, there's a lot of insoluble hydroxides. So the ones that are soluble are going to be the ones that are paired with group 1A. So lithium, sodium, and all those. So lithium hydroxide, sodium hydroxide, potassium, rubidium, cesium. All these group 1A hydroxides are soluble because all group 1A cations are soluble. And then there's a few exceptions also that we talked about in group 2A, which is going to be calcium, strontium, and barium. So pretty much every other hydroxide salt is insoluble, so they wouldn't be considered strong bases. But any of these which you can dissolve in water are considered strong bases because when they dissolve, they release OH minus into solution. And then we also have weak acids and weak bases. And so these are the ones that don't completely dissociate. So they release some ions into solution, but they don't completely dissociate. Remember, dissociate means to break up into ions. So basically what this means is that most of the molecules, so we dissolve these compounds in water, and most of the molecules remain intact. In most cases, you're not breaking them up into cations or anions. You have intact neutral molecules as the major species. All right, so the weak acids are basically every other acid besides the strong ones. So I gave you a list of strong acids up here. Any other acid that we would think about is going to be a weak one. So the weak acids that you're most likely going to come across are HF, H3PO4, and then acetic acid, CH3COOH, which is sometimes written as HC2H3O2. So that acetic acid. Those are the three most common weak acids. There's only one weak base you have to be familiar with in this course. Eventually, you'll learn a lot. You'll learn some more of these if you take organic chemistry. There's a lot of weak bases that are organic compounds. But the weak base that we'll talk about in here is just ammonia and H3. Now, it may not be obvious. Why is this a weak base? It doesn't have any OH minus in it, so how does that work? You know, if a base has to release OH minus in water. So what happens with ammonia, which again, not terribly important for this course, but ammonia reacts with water when you dissolve it. And so one of the hydrogens gets transferred from water to the ammonia, and so you get NH4 plus ammonium and OH minus. So again, this doesn't go completely to the product side. Most of the NH3 is still intact as a neutral molecule, but you get some dissociation to make NH4 plus and OH minus. And because you're releasing OH minus, that's going to make the solution a base. All right, so those are weak acids and weak bases, and we want to make sure we're at least a little bit familiar with the distinction between those. But the more important thing is talking about what happens when acids and bases react with each other. And so, of course, we call these acid-base reactions. And the net ionic equation for an acid-base reaction is always the same. No matter which acid and which base you're reacting with each other, they're going to give the exact same net ionic equation. So sometimes it's helpful to think about that as a starting point. So all we're doing with an acid-base reaction is we're taking the H plus from the acid, remember that all acids release H plus in solution, and we're combining it with the OH minus that comes from the base. So that gives us a net ionic equation that looks pretty simple, and it's going to be the same for every acid-base reaction. I should say almost every acid-base reaction, because sometimes acid-base reactions are accompanied by precipitation, in which case the net ionic equation looks a little bit different. But just about all acid-base reactions have the same net ionic equation, which is that H plus, which comes from the acid, reacting with OH minus from the base, and you're just making water. So it's recombining H plus and OH minus to make water. Okay, so that's what the net ionic equation usually looks like. And then the identity of the spectator ions and the coefficients for the full balanced reaction really depend on what the identity of the acid and the base are. So there will be some spectator ions involved, and sometimes these acid-base reactions are going to have small coefficients like we saw for precipitation reactions, but what those are depends on the identity of the acid and the base. Alright, so then if we want to write sort of the total equation for an acid-base reaction, so this is the net ionic equation, but if we're interested in what else is going on, acid-base reactions always have the same form. You have your acid and your base reacting with each other, and the two products, you're always going to make water from an acid-base reaction. So again, the H plus and the OH minus combine to form water as part of the reaction. And then the other thing is you have the ions. The acid has an anion associated with it. The base has a cation associated with it, and so you're going to also form an ionic compound as one of the products. Or a simpler way to say this is acid plus base makes salt plus water, where salt is an ionic compound. So when you have this ionic compound as one of your products, the cation comes from the base, so the base is usually going to be a hydroxide salt which has some cation associated with it. And then you're going to have the anion coming from the acid. So whatever's paired with H plus is going to then end up as an ionic compound in the product. Alright, so that's the general form of an acid-base reaction. So let's just look at a couple examples of these. And again, they can have coefficients, but they're usually pretty small and pretty simple to balance. And there's even a trick for balancing these that I'll show you. So let's say we have nitric acid with potassium hydroxide. So we need to be familiar also with the formulas for acids, because that's going to come back in this part of the course. So if you have nitric acid, that's going to be the acid of nitrate, which is NO3 minus. So it's going to be HNO3. All right, so nitric acid is HNO3. We take that, we combine it with potassium hydroxide, which is KOH, two soluble compounds. And then when they react, again, the product is always going to be a water and an ionic compound. So water is our first product. And then the ionic compound that forms, we're going to take the anion from our acid, which is NO3 minus, and we're going to pair it with the cation from our base, which is K plus. So we just get K plus paired with NO3 minus, which makes KNO3. This is a soluble ionic compound, so it's also going to then remain in solution as an aqueous species. So this is a 1-to-1-to-1 reaction. There's no coefficients here. Everything is a coefficient of 1. And a fast way to determine that, which we'll see in the next one also, is that our acid has 1 H plus, our base has 1 OH minus, so we know they're going to react in a 1-to-1 ratio. If you have the same number of H pluses and the same number of OH minuses, those are always going to combine to form water. So if you have one of each, they just have coefficients of 1, and then we don't have to write any other coefficients on the product side either to balance this out. But then sometimes they react in more complicated ratios. Again, nothing more complicated than usually 1 to 2 or 2 to 3 at the worst. So if we have sulfuric acid and potassium hydroxide, sulfuric acid has a formula of H2SO4 because SO4 has a 2 minus charge, so it needs 2 H pluses to pair with it. So if sulfuric acid is H2SO4, KOH is still KOH, potassium hydroxide. The products are going to be water. And then the ionic compound that forms, we have K plus from our base pairing with SO4 2 minus from the acid, so it's going to be K2SO4. So we're always writing these to make completely neutral ionic compounds, so K2SO4. Now we have to put some coefficients here, and again, the fast way to think about the coefficients is to look at the number of H pluses and the number of OH minuses. So H2SO4 has 2 H pluses, OH minus only has KOH only has 1 OH minus. Those need to combine in an equal ratio, so we need to have 2 OH minuses to react with the 2 H pluses. So if you have 2 H pluses from H2SO4, we need 2 OH minuses from KOH, so we put a 2 in front of it. If 2 of each are reacting, that means we form 2 waters, and then this one is already balanced out. 2 potassiums, 1 sulfate, 1 sulfate. So balancing the reactant side is usually a good place to start with. And again, we want to make sure that H plus and OH minus react in equal amounts. So if we have 2 H pluses in our acid, we need to also then make sure there are 2 OH minuses provided to react with that completely. So that's how we balance acid-base reactions, and we'll see a lot of examples of that as we go and do this. Alright, so then we have an example here about net ionic equations. So as I mentioned, most net ionic equations for acid-base reactions are the same, but there are some exceptions, and those exceptions usually involve weak acids. So here we want to know the net ionic equation for the reaction between acetic acid and barium hydroxide. So we have CH3COOH is acetic acid. We should be aware that acetic acid only has one H+. So these three hydrogens don't react as acids, only the one that's attached to oxygen does. That's why I wrote it this way. So make sure you remember that. Acetic acid is a monoprotic acid. It only has one H+. And that's going to combine with barium hydroxide, BaOH2. Then we're going to form products, water. And then the ionic compound that forms is going to be barium 2 plus paired with acetate, which is CH3COO minus. So we need to have two of those to balance the charge. So barium acetate, 2 plus cation, 1 minus anion, so they combine in a 1 to 2 ratio. This is going to be soluble because all acetate compounds are soluble. And if we write the total ionic equation, so we're trying to find the net ionic equation, so the second step is always to write the total ionic equation. This is where we have to be careful with weak acids. So acetic acid is a weak acid, which means the vast majority of acetic acid exists intact in solution, CH3COOH. We have some H pluses and some acetates, but the vast majority of CH3COOH is going to be intact as a covalent molecule. So whenever we have weak acids, we don't separate those for the total ionic equation. The weak acid stays intact. I guess I forgot to balance this. We should have a 2 up here and a 2 there to balance this. But anyway, for the total ionic equation, we have to recognize that acetic acid is a weak acid, so we don't separate it into ions. All right, so the reason I'm introducing this example is to show you this distinction with weak acids. So when we have the total ionic equation, CH3COOH we don't do anything with. It remains intact, or the vast majority of it remains intact. But then if we look at our other reactant, which is barium hydroxide, that's a soluble hydroxide compound. So that one we split up. It's an ionic compound, so just like we saw before, it splits into its ions, which are barium 2 plus, 2 OH minuses. And then on the product side, water is a covalent compound, so we don't separate that up into ions. Remember that only strong acids or soluble ionic compounds get separated, so we have 2 H2Os. We don't do anything with that. And then our other product, barium acetate, is a soluble ionic compound, so we get barium 2 plus, and then 2 acetates, CH3COO minus, also as a product. So anything that's a soluble ionic compound we can separate, but anything that's a weak acid or a covalent compound remains intact. So then finally for the net ionic equation, we just have to remove those spectator ions that appear on both sides. And in this case, there's only one spectator ion. So the only species that's a soluble ion in the same form on both sides is barium 2 plus. So that we can remove to write the net ionic equation, but we don't have any other spectator ions here. OH minus combines with the H plus to form water. Acetic acid and acetate are interconverting, so you don't have acetate on both sides. And so that's going to be our only spectator ion is barium 2 plus. So for the net ionic equation, all we have is 2CH3COOH plus 2 OH minus combining to form 2 CH3COO minus plus 2 waters. And as we see here, sometimes when you're writing the net ionic equation, you can get coefficients that reduce. So really a simpler way to write the ionic equation, every single species here has a coefficient of 2, so we can just remove all those and write them as coefficients of 1. So this becomes CH3COOH and we just get rid of the coefficients and the same reactants and products. All right, so if we're writing the reaction with the lowest whole number coefficients, this is how we would want to do it. So the series of steps is exactly the same. We just write out the full equation. We separate out anything that's a soluble ionic compound or a strong acid into ions, and then we remove the spectator ions to get our final form. All right, let's look at one other example here, that an acid-base reaction that involves precipitation. So as I mentioned, it is possible sometimes that in an acid-base reaction you form an ionic compound that is insoluble, so the acid-base reaction is going to be accompanied with precipitation. So an example here would be phosphoric acid and calcium hydroxide. So phosphoric acid is H3PO4, phosphate is PO4 3-. We have calcium hydroxide, CaOH2, calcium is 2+. And this goes to Ca3PO42. So the calcium 2+ is going to be paired with phosphate 3- to make an ionic compound. And then we're going to make water as our other product. All right, so first thing we can do is think about the speciation here. So calcium phosphate, almost all phosphates are insoluble unless it's paired with sodium, potassium, or one of those. So this is going to be a precipitate and this is going to be liquid. And then to balance this, we have 3 H pluses from our acid, H3PO4. We have 2 OH minuses from our base, calcium OH2. We need to have equal numbers of each. So if we put a coefficient of 2 in front of here, we'll have a total of 6 H pluses. And then if we put a coefficient of 3 in front of our base, we'll have a total of 6 OH minuses, 3 times 2. So we need the H plus and the OH minus to be balanced. So we have to put a coefficient of 2 here, a coefficient of 3 here. That's as complicated as the coefficients we'll ever get for an acid-base reaction, so it doesn't get any more complicated than this, 2s and 3s. And then if we look at the product side, we have our ionic compound is already balanced, 3 calciums, 2 phosphates, but if we're combining 6 H pluses with 6 OH minuses, we're going to make 6 H2Os. All right, so you can kind of balance these by inspection, but if we think about the ratio of H plus and OH minus, it can help us write out coefficients a little bit faster in some cases. So if we think about what we have going on here, this is a weak acid. This is a soluble ionic compound. This, as we said, is insoluble. And this is a covalent compound. So when we write an ionic equation, the only thing we want to separate are soluble ionic compounds and strong acids. We only have one soluble ionic compound here, so our total ionic equation is going to look just like this. H3PO4 is a weak acid, so we don't separate it. We have our one soluble ionic compound, which is going to make 3 calcium 2+, and then it's going to have 6 OH minuses, 3 times 2, total of 6 OH minuses. And then on the product side, we don't separate anything because we have an insoluble compound which remains intact, and then we have 6 waters, which is covalent, so we don't separate that out into any ions. And so this is our total ionic equation, and if we look here, we don't have any spectator ions in this equation because the calcium 2+ forms an insoluble ionic compound, so you don't have calcium 2+ on the product side. OH minus no longer exists on the product side. There are no spectator ions. And when you have this situation, which is fairly rare, that means the total and the net ionic equations are the same. So we don't have any spectator ions to remove, so the net ionic equation looks exactly like what I showed above. So the total and net ionic equations are the same. And so this equation here is both our total and our net ionic equation. We still have to separate out the soluble compounds, but we don't have any spectator ions to remove, so the net ionic equation has the exact same form. All right, I will stop there, and I'll do the last one on my own and put it in the notes. And so I'll see you on Friday, where we'll talk about the third category of reactions, redox reactions.